Hi everyone, and welcome to Functional February, the first themed month of the 12 in 23 challenge. Now, if you've got no idea what I'm talking about when I say 12 and 23, I'll link to a couple of videos in the description to give you more info. But fundamentally, we're challenging you to try 12 different languages during 2023. Each month has a different theme, and this month is all about functional programming languages. Now, this video is in two parts. The first half, I'm going to tell you about how Functional February is going to work on Exercism and what we've got in store for you. And then in the second half, I'm going to dig into what makes functional programming languages interesting with Erik, our head of open source at Exercism. And that's going to be a fun conversation that we recorded a few days ago. So, firstly, the aim of this month. Well, it's for you to try out functional languages, or if you've already worked on them before, then just to go a little bit deeper. Explore the unique ideas to functional languages, things like pattern matching, immutability, higher order functions. Learn how to think in a functional way, and most importantly, have some fun experimenting and playing around. We've selected 9 languages that we're focusing on this month, and we're recommending that you start with one of Elixir, F# or Clojure, all of which have great learning modes on Exercism. Elixir in particular is one of the most detailed and refined tracks in the whole site. There's 57 concepts there to learn. Then the other 6 languages are Erlang, Haskell, OCaml, Scala, Standard ML, and the newest language on Exercism, Gleam. Now, for many people, the first question they're asking about Functional February is how to get the badge for the month. Every month has a badge. Well, it's pretty simple. Choose one of the languages I've just mentioned and solve and publish 5 exercises in it. You can choose any exercise, other than Hello World, but we recommend a few specific exercises that will be really good for practicing functional traits. The first is Hamming, to explore higher order functions. Then Collat's Conjecture, to practice recursion. Robot Simulator, to play with immutability. And then both Yacht and Protein Translation for pattern matching and higher order functions. All of those are listed on the 12 in 23 page, so you can check that out later and have a look. So aside from solving exercises, what else do we have in store for you? Well, firstly, we have a couple of big interviews planned. Top of the list is a chat with Jose Valium, the creator of Elixir. I'm going to be chatting to Jose, exploring why he chose to make Elixir a functional language and putting your questions to him. And then secondly, I'm speaking to Louis Pilfold, the creator of one of the newest functional languages out there, Gleam. Louis is also going to be streaming himself solving Gleam exercises on Exercism throughout the month, so you'll be able to see how he thinks about functional programming. We really want this to be a month where we're learning together, and as part of that, we want to encourage the community, you, to share experiences of functional programming. So to facilitate that throughout the month, we're going to be live streaming a mixture of walkthroughs and exercise solving sessions with contributors across all of our featured languages. All of this streaming is going to be on our brand new Twitch channel, which is Exercism Live. So please subscribe over there so that you don't miss anything. We'll also be adding a widget to the main site dashboard so you can keep an eye on that as well. Then on the Exercism forums, as well as just general conversation about functional languages and helping each other when we get stuck, we're also going to be having an official thread putting together all of the best resources for learning and understanding and exploring functional programming languages. So if you're a bit more of a seasoned functional programming developer, please come along and tell us some of the resources that helps you when you were learning so that we can all learn from those together. We're also going to have some exclusive Functional February swag, which is only going to be available this month. We've not finished making it yet, so keep an eye out for when we launch that and make sure you get your hands on it this month. And then 2 final things before we jump into the conversation I had with Exercism. Firstly, not enough people are requesting mentoring. If you're not, you're massively missing out. When you solve an exercise in a language you don't know well, mentoring should really be the first thing you reach for on Exercism. Having someone who's more experienced than you, giving you personalised pointers and tips, is just an unbelievable way to level up. On an Exercism, it's totally free and it's loads of fun. So this month, when you solve an exercise and you're not sure if you've written it like a functional programming pro, request mentoring and get someone who's more senior to come along and help you out. Secondly, Exercism needs donations to survive. We're a not-for-profit organisation. We're trying to help as many people as we can, and we do that for free so that anyone in whatever situation they're in can learn. If you're fortunate enough to find yourself in a good financial situation right now and you can spare some money to support our work, please do consider donating. Frankly, if people don't support us, we're not going to survive. If you can't support us, that's absolutely fine. That's why we're free, so that people who couldn't afford Exercism otherwise can still get access to it. And then finally, if you've already donated, just thank you so much. It absolutely means the world to us, so thank you. Now we're going to not very seamlessly segue into my conversation with Erik. Thanks for watching this first half. I hope you have a great functional February, and please do get involved in the comments below and on Exercism's forums as well. Thanks. Let's kick off the month, and we're going to be joined by Erik Schierboom, Exercism's head of open source, who is going to introduce us to the theme of the month and tell us how to make the most of it. Hi, Erik.
Hi, Jeremy.
So, functional programming. I know you're a massive fan of functional programming. Before we get into the nitty-gritty details, it'd be nice to know just a little about what you like about functional languages, why you think they're enjoyable, fun, why they're interesting to you.
Yeah, sure. The reason why I like functional programming languages is because it's what's in the name. It's fun. And to me, there are several reasons why they're fun. For one, what I really like is that they're easy to reason about. And this has a couple of reasons. For one, it has immutability, usually at its core, and it reduces a focus on side effects. So I found that these two things, with these two features, you can separate behavior from data, and that makes for an easier mental model than objects with state to me. So that makes it easier to think about your code. And most functional languages also have very powerful type systems. And these type systems help you prevent common mistakes like null pointer exceptions, etc., or forgetting a case statement in a switch, etc. So it's not a feature that all languages have, but most of them do. And what I also really like is that functional languages are usually very concise, but still very expressive. So features like sum types, pattern matching, type inference, list comprehensions, and a lot of built-in higher order functions all give you this terseness, this conciseness, while still being very expressive. So you can do a lot with very little code. And I quite like that, especially with a lot of the Exercism exercises. And my final thing is that I think that functional languages are often at the cutting edge of innovation. So for example, Unison is a great example with content address code. F# has type providers, and Idris has dependent types. So.
Awesome. There's a lot to love there. I know it's something that you're really passionate about. I think it would be good to start off by sort of just explaining to people who haven't really maybe used functional languages exactly what they are. I mean, we know that functional languages are languages that have functions in them, but a true functional language is one that takes that idea much further. Functions become the central axis that everything else revolves around. And unlike in, imperative programming, where we tend to think of functions like maybe procedures or just chunks of code, in functional programming languages, functions are the true first-degree citizens. And it'd be really good just to dig into this a little bit and just talk a little bit about what it means for functions to be first-degree citizens in a language.
So functions being first-class citizens means that you can work with them the way that you're used to with common data types like Booleans and integers. And for example, you can use them as parameters. So you can pass in a function as a parameter. You can return a function from a function. You can define functions within functions, like nesting. And you can assign them to variables, or sometimes in the functional language, they call them bindings because they usually don't change. But it's basically functions are a thing. They're not just a thing that you can execute. It's also a thing that you can work with. You can create functions from functions, etc. So there's a lot of things that you can do with function that you might not be able to do in non-functional languages. So let's look at some code. Let's start by doing a binding. So we'll assign the value of 3 to B, assign 4 to A, and let C is A plus B. So this doesn't really do much. So let's just ensure that my math is correct. It should be 7. Okay, we'll see it returns 7. We can rewrite this by creating a function. So the function is adder. It will take an x and a y, and it will return x plus y. Nothing much going on, of course, here, just a function that adds 2 numbers. And instead of doing this, we can do adder, and then we'll pass in a and b. So this should have the same result, because we're merely forwarding these values to this function, which did the same thing that we had previously. So it should still be 7. Yep, okay, good. Not really interesting, but I told you that you could assign functions to values too. So what I could do is I could say, let my adder be equal to adder. So what we're doing here is this name, my adder, is pointing to the adder function. So you could almost say it is the adder function, but it's like a reference. You can sort of think of it as the same thing. So what we can do is, instead of calling adder, we can call my adder. So remember, my adder is just pointing to the adder function. So think of it as like indirection, but it should work. So let's run this. And we can see it's still 7. So what this shows you is that you can assign functions to variables, and then you can work with them. So let's try something else. Let's try and return a function from a function. So let's say we have a new function called createAdder. Doesn't take any arguments, but what it will do is it will return a new function. So within the createAdder function, we can create a function. So let nested adder, so nested because it's defined within a function. It takes an x and a y and returns x plus y. So this is a function, and we can return it just like we do with any other values. So in F#, the last value in a function is returned, so last expression. So let's recap this a bit before we continue. We have a createAdder function that doesn't take any parameters, but its return value is a function. So within the createAdder function, we define a nested adder function, just a simple function, x and a y value, returning the plus, and that's the thing that we return. So this is a function. So if we do createAdder without any function, any arguments, and assign that to createAdder, then createAdder is the same thing as this. So calling this will internally create the function, and then it will return it. So we then assign it to this binding, and we can use it like the regular add function that we had. So if we run this, we should still have the same result, and we do. So it's important to understand what's happening here. So we're calling a function, and during execution, that function will create a nested function, and it will return that function. So the function is an object, a thing that you return, and you can assign it to values. We already saw that we could assign a function to a binding here, and we're simply doing the same thing here. Only the fact that the function is defined within another function is basically an implementation detail. We don't care. We just care that it's a function that is returned by a function. And we can create it like that. So the final thing that I would like to show you is that you can also pass functions as an argument. So we'll say call adder, and we'll take in the function and an x and a y, and then we'll do adder func x y. So I'm gonna remove a bit of the old code here. So we'll uncomment this, and let's focus on this bit. So this is a function we call adder, and it takes 3 arguments now. The first one is the adder function that it should call, and the second is the x, and the third is the y. So add a function is actually a function that we pass in. So do we have a function that takes an x and a y parameter? We do. We have adder. So what we can do, if we call the call adder function with the first argument is the function, well, we have a function called adder, and then we pass in a and b. This will, in the end, gets translated to just this. Oh, sorry, to this. That's the same thing, but we do it via indirection, just to show you that you can pass in a function as an argument to a different function. So let's run this again. And it's still 7, so it still works. And what this function shows you is that it's just as normal as passing in a number or a string, is that you can pass in a function as an argument. And that way you can build building blocks of functions and then pass them to other functions to reuse them. So this is a very modular way in which you can build out your code base by having smaller functions build larger functions. So this is really, really helpful. It usually is quite odd if you're not used to working with functions like regular variables. So it can take some getting used to, but once you've mastered it, it's really flexible. And I find it quite liberating to be able to work with functions just like you do with numbers and strings, because it's all the same thing, basically. You don't have to make exceptions for functions. So this is a key thing that all functional programming languages have, is that functions are so core, so key, that you can use them like any other values, which is functions as first-class citizens.
Nice. And what programming language is this for anyone watching?
Oh, sorry about that. This programming language is F#.
Okay.
So it's
one
of my favorites. Spoiler alert.
Yeah, Erik's the maintainer of F# on Exercism. So I think we'll be looking at a few more F# examples. Cool. So, I mean, there's probably a lot for someone to take in if you're just looking at this and you've not come across that before. But, you know, the concept here that Erik's demonstrating about the idea that you can be passing functions around in the same way that you would be passing any other variable around is the key thing, and that you can build functions that take functions and build on those functions, compose them together. So, yeah, it's a fascinating way of thinking that's so different to what a lot of people will be used to. And functions like this in functional programming languages, they tend to be pure functions. Can you explain, Erik, how that differs from, well, I guess, non-pure functions in other programming languages?
Yeah, sure. Well, this actually is somewhat related to functional languages having a strong mathematical basis. So if you might recall your math lessons in high school or something like that, a function can only ever do something with what you put into it. There's no global state in math. So a function only can work with what you pass into it. And that's basically what a pure function also is. So you define a function, you define 0 or more parameters, and the only thing that it can work with are the values of those parameters. So this means it's very clear what a pure function does. So we call this pure functions because they don't have side effects. Because what side effects means, it's doing something with the global state, and a pure function shouldn't be doing that. And part of that is just working with the input parameters, but part of it is also not doing IO or whatever. So things that are that you don't return, basically. And that's also the reason why pure functions are actually nice to work with for several. So the biggest one is that they're easy to reason about, because everything that's being used within the pure function is either the parameters or something that you are doing with intermediate values or something like that. So there is no such thing as a global state. So you can easily test them because, well, the only thing that you can actually change are the input parameters. So you don't have to set up any other mocks or whatever, just the inputs, and then you have an output. So, and this also means that you could theoretically do execution using pen and paper because, well, it is sort of like a mathematical function. Although don't get to drill down into the math bit, because you don't actually need to know math or anything like that. It's a common misconception about functional programming. Yes, there is a mathematical basis, but other languages have that too. So you don't have to know anything about math. But it is very easy to work with pure functions. They're easy to test. You can even do, maybe if you're very advanced, you can do formal verification, because you can model how a function works, because it's like a regular mathematical function. And then you can sort of see that, hey, if I pass in this, you can just do the execution bits, probably not using pen and paper, but probably using like a model checker or something like that. And then you can verify that if you pass in these values, the output is always the same. Mm-hmm. So the fact that it's always the same if you pass in the same values makes it really predictable. So there will never be any surprise. And it also means that if you've calculated something with the same value, if you call the same function twice with the same values, you could theoretically only calculate it once, and the second time know that, hey, this function was already called with those values. I can just return the previous result, because as it is only working with the input parameters, you always get the same result back. So you could do caching, etc. Memoization is what they call this in a fancy word, but it's basically just caching. So let's look at some example code. We have some C# code here, and this function violates both properties of a pure function. For one, it does write to the console, so that's a side effect. And the second thing that it does is that it uses datetime.now, which is apparently available somewhere. This doesn't get passed in as a parameter, but it's apparently there. And it means that if you call this function twice, datetime.now could be different. So calling it with the same values, which is in this case no parameters, can give you different results depending on the time of day. So this makes it impure and harder to reason about, because you don't know what to expect, basically. So let's look at some F# code that's completely equivalent to this, and then see how we can make that into a pure function. So we have an isMorning function, no parameters, and it writes to the console and has the same datetime check. So the easy thing to do is to first get rid of the console write line. So that's easy enough. Now we don't have any side effects, so that's good. For the second property, where we don't rely on anything else but the parameters, it's actually quite clear what we need to do, because we're using a datetime to calculate the result value. So, but instead of using global state, we want to have that be a parameter. So we'll add a parameter, and we'll make it of type datetime, and then we'll replace the datetime.now calls with our time parameter. And with that, we've actually got rid of the global state that we were using, and we are now using our parameter, which means that this function, as it is only using that parameter to calculate the output value, is now completely predictable. It is satisfying property 1, because if you pass in the same datetime argument, you'll always get the same result. So this function is now deterministic, it's easy to test. You could possibly cache things, because if you've calculated something once, it will, for a specific argument, it will always give you the same value back. So we now have a pure function with all the benefits that come from it.
And so, to my mind, the final big thing, and you touched on this very briefly when you started talking, but that functional languages have in common is that data is usually immutable by default, which is a huge change from lots of programming that many people, myself included, use day to day, where changing and manipulating variables is very much at the heart of everything. Do you want to talk a little bit about this, what you see as like the pros and cons of immutability? I know it's, again, something that you're a fan of. Interested to hear your thoughts, Erik.
Yeah, so the language that I started learning with all were mutable by default, like C and C++, etc. But functional languages are usually have the reverse, so where data is immutable by default. And this means that once you assign a value to a name, like what you call a variable in most languages, or a binding in a functional language, that name will always refer to the same value. It will never change. So whether or not you're looking at the same name, maybe 100 lines of code later, you will be guaranteed that it still has the same value that it originally had. So it's like a permanent binding of the value. And this has a lot of advantages. for one, it's very easy to reason about. So if you know that you initialize a certain binding to a value, I don't know, 2, you know that it will always have that same value. So you don't have to scan all those lines of code and maybe, if for example, in C# code, I might have to, I call a function and it might change the value. So there's a lot of things that I have to keep in my head. So like you can almost see it like bookkeeping that you need to keep track of. Whereas with immutable values, that's all gone because, well, you do have to remember the actual value, but it's very easy because it won't ever change. And this is not just with variables / bindings. This is also the case with data structures often. So in functional language, the most commonly used data structure is a list, which is like a dynamic array. But the list is actually immutable. So if you have, I don't know, a list of names, adding a new name to the list means actually creating a new list. So you're not modifying the existing value, but you're getting a new value, which is like a copy with an additional value. So the immutability is not just there for variables / bindings, but also for data structures and also for things like, it's not classes, but you have records or there are different names for it, but basically like a grouping of data types. So for example, a person would have a name and maybe an age. So this grouping, let's call it a record for now, will also be immutable. So if you want to change a person's name, you can't actually change its value. You have to return a new a copy of the record, and then you change its value within the copy. So it's completely different actually than what you're used to. We're so used to everything being mutable and having state, etc., because object orientation is probably the most widely used paradigm, I think. But a core tenet is there that you have state, classes have state, and you mutate state via methods. And with functional programming, that's completely different because you're working with data, and data doesn't have behavior attached to it because it's immutable. So you can't have mutating method on it. You could have methods on it that, I don't know, return values or return new objects, but you can't actually mutate. So the common way in which in functional language where you work with data is that you have functions that have the behavior, and data is just that. It's just data. It's just a collection of, I don't know, primitives like numbers or strings or something like that. So it's a very different way of looking at things. So with object orientation, your data and your behavior are mushed together. So they're close to each other. Whereas with functional languages, they are separate. So you have data and you have functions that work on that data, which are the behavior. So it's a different way of looking at it, and there are pros and cons for both. But one of the benefits of having immutable data is that it's very good for concurrency. So if you have multiple processes, threads, or whatever actors, you are guaranteed that it's safe to send data over the line to other processes or threads because it can't change. The problem with concurrency is multiple things, threads, processes, changing the same thing. So you might be expecting it to be in a certain state, but something else could have changed it in the meantime. So, but with immutable data, you don't have that issue because you can't. So the data is always fixed. So it's great for concurrency purposes, actually. And one final thing that I wanted to mention on immutability is that because you have to assign a value to a binding, you mean you can't define a binding and then later on set its value because it will be changing something, because what will be its initial value. So what a lot of functional languages do is they completely get rid of null, actually. So there's no null or nil, whatever your language uses, as you also are, because you are required to initialize a binding to a value. And often they say, hey, well, then we don't even need null. And languages functional language often have like a separate construct for that, but you don't have null pointers then. So it's not directly tied to immutability, but it's often a result of that because you always initialize your values or /bindings. So
very cool.
There are hard. Oh, sorry.
No, go on.
There are hard things with immutability, though. So if you're used to working with mutable things, like in a language like C# or Java, everything is mutable, and you have certain patterns that you use, like a for loop or maybe state in a class, looping over an array and changing its values. But then if you go to a functional world where that is not possible, so you can iterate over an array, but you can't change its values. So how do you do something like that? And you can't just have like a mutable value where you keep on adding things, etc. So there are different patterns that you have to learn to work around these things that you can't do anymore because of the immutability. And when I started out doing functional programming, I found those things really hard. So you're so used to doing things in a certain way that you have to learn things, how to do things differently. And the whole mutation, immutability thing was one of the key things that were hard for me personally when I was learning functional programming. And I can see other people maybe having the same experiences. And historically, a downside of immutability is performance. So it's less so currently, but you can see that if you have an array of, 10,000 names, and then you want to add a new one and you get a completely new copy of that array with an additional value, that you would have duplicate memory plus one extra item. Well, in practice, it's not entirely, this is not how most immutable data structures work, because as it can never change, you can say that the second copy is like the first one with an additional element, but it's still, there is a little bit overhead in the immutable data structures. So you have to be careful whether or not immutability is a thing for your performance. It could be, it is probably not the case for most purposes, but it's still something to look into. I've done advent of code stuff with F#, and when things were really slow, one of the first things that I would do is to replace the immutable data structures with mutable ones, and they would basically always be faster. Because there's some optimization stuff that you can't do with immutability that you can do with mutation. So, but for readability and reasoning, I still like the immutable data structures, but it's something to consider. We have some C# code here in which a variable defined P is defined, and P is an instance of the point class. What we're doing here is we're calling the constructor of the point class with 4 as the X value and 6 as the Y value. So very typical object-oriented constructor call. As classes have state, you can also mutate stuff. So what we can do is we can dot into the X property here and assign it the value 5. So we're updating the X value of the P instance. So what we're showing here is that classes have state, and you can mutate them. So if we were to do this, this would evaluate to true because we've changed the state of P. This is all very typical object-oriented behavior, so nothing really fancy here. The only thing that you might be confused about is the property syntax, but you can read that as it being like a regular setter method. So it's equivalent to this code. So let's see what the same code would look like in F#. Syntax is slightly different. We're using let. We haven't used a new keyword because that's optional, but we're still creating a new point instance with X is 4 and Y is 6. On the second line, what we do here is we try to update the X value. In F# you do that using the left arrow operator, but you probably noticed the red squigglies, which is bad because apparently this doesn't even compile. So if we try to compile this, we get a helpful error message. And it says a value must be mutable in order to mutate the contents. So let's see how we can fix this. So the best way, so the default way to fix it is by adding a mutable modifier. So now we have made P mutable. And this shows you that in F#, things are immutable by default. If you want to mutate things, you need to opt into that behavior by the mutable keyword. So this code is now fine. So if you run this, we should be seeing that it outputs the updated X value, which is 5. And indeed, it does exactly that. So that's good. A more functional way is if we somehow need a second value, but with the same Y value, but a different X, we could do this. We could do n is point, and we'll use the other value, the specific 5 value, and we'll use P's Y value for the Y. And then we have two immutable values. They have the same Y value, but they have different X values. So this is a immutable variant, and this might not be perfect in all situations, but it's very easy to reason about, because if we're printing P here, we know that its X value will be 4 and its Y value will be 6. So this is a key benefit of immutability. Regardless of what happens, if a value is immutable, it will always have the same value as it had at its definition. So that's very easy to reason about, and I think reduces the likelihood of bugs.
So another big feature that you find in functional programming languages is pattern matching. This is something that tends to blow people's mind when they start out with it and first see us. Can you show us some good examples of this?
Yeah, sure. Let me start with explaining what pattern matching gives you. So I think the majority of people will probably be familiar with a switch statement, which you have in C, C++, and a lot of other languages. And usually what a switch statement allows you to do is you say, hey, I want to switch on a value. And then there's a list of cases, which are constant values. And the switch statement basically says, hey, if this matches the value that you're switching on, then do execute this code, etc. But the limitation is usually that the things that you can switch on have to be primitive types, like numbers or booleans or strings. You can't switch on a class or something like that, or I don't know, something else, or a list. But with pattern matching, it's basically like a switch on steroids. So you can do a lot more than just, you can also match on constant values, but you can also match things like lists. So is this an empty list? Does it have 2 elements? Is the first element like, I don't know, pattern Y? You have tuples, you can match on different types, objects, and you can often use guards, which is like, only I have this pattern that matches, but only if it also has this Boolean condition evaluate to true. But this might be slightly vague, so I probably should be showing code. And we'll use F# as our example language. Let's define a list of numbers. We'll do that like this, 1, 2, 3. So a list with 3 numbers. In an imperative way, we could check if the list has 3 numbers and the first one is a 1. The following way, if numbers.length equals 3 and the first element equals 1, then print, I don't know, correct. This is fine. So this is not too bad. It's quite readable. It's somewhat clear. But you can also do this with pattern matching. So we'll put this in a comment. So we'll do match. And match is the F# keyword for pattern matching with, and then we'll do the type sign. And then this is basically like the case. Now we define the pattern. So we're saying we want to match on the list. So we're using the brackets. We're saying the first value has to be a 1. I don't care about the second value, and I don't care about the third value. And you can then do the right arrow sign, and this is the code that gets executed when the pattern matches. And this will print this exact same thing as the code that we had here, but this is a lot more concise. And it's not only more concise, the thing that is great is that this pattern is very reminiscent. It uses almost the exact same syntax as the way that we defined the function. The only thing that we're differently is that we're using discards here. So pattern matching is usually very similar to how you're already using the data type. So there's no new syntax to learn. You're just reusing what you already know. So let's look at a different type. So let's look at bools. So we'll have a tuple, so of two booleans, so true and false. And a tuple is a pair in this case. So we have two values which could have different types. So you could have a tuple of one being a boolean and one being a number, but we'll just have two booleans here. And let's pattern match on that. So bools with, so let's say if it's true and false, the parentheses are optional, but I'm going to keep them just because it looks good here. And then we'll say t/f true/false. And this works too. So the way that you work with tuples is again very reminiscent of the way that you define tuples. The compiler will note something though. It says incomplete pattern matches. And this is something that many functional languages have, in that if you use pattern matching, the compiler is smart enough to understand if you have covered all the bases. So it knows that a boolean can be either a true or false. So there are actually 4 different cases that we need to handle here. Well, need to is a strong word. We can ignore the warning, but I would encourage you not to. So false, true, true, true. And now the message goes away. So the compiler has helped us identify that we forgot, or maybe intentionally, to handle the default case. And we have now added everything, and this is obviously not doable if we change this to a number, because then we can't possibly match all the numbers. So what we could do then is, well, let's just match this on true and 1. Say, hey, for all the other cases, not interested. We'll just use the underscore, and the underscore is like a catch-all. It doesn't matter what the value is, this will always match. Okay, so let's try one other feature. So let's say we have nums, we'll have 2 booleans. And what we're going to do is, what we're going to try and do is to say, hey, we want to match this, but only if the second value is greater than 5. This is something slightly ridiculous, but who knows. So we'll call this y, and we'll then add a different clause, a guard clause. So we're saying like this. So we're using a regular pattern. The 2 is a constant value, so it has to match. So if this is a different value than 2, it won't match. But the y is a variable pattern, so it will always match. And in the process of matching, it will assign the value to y, which means that we could use it here. We could work with y here, which can be very cool. But we can also use the value in a guard clause. So this is saying only match this clause when this is the same pattern and y is greater than 5. So we're saying 2, y greater than y greater than 5. So if we pass in 2 and 1, this won't match because y will be set to 1 and 1 isn't greater than 5. So it's perfectly fine to have this. So it's less than or equal to 5. We don't have a guard clause here, and this shows you that clauses of pattern matching works from top to bottom. So we will try to match this one first, but if it doesn't, it will move to the next one, etc., etc. So the order of things in a pattern matching in clauses, it matters a lot. It's always top to bottom. So we don't need the y here, so we can do the underscore, same thing that we did before. But you can see how powerful pattern matching is because you can use it on different types. You can use guard clauses. It has syntax that is very reminiscent of the way that you're already using the data types. And it has usually has things like exhaustiveness checking, where it detects if you haven't covered all the bases, which helps prevent mistakes. So all in all, pattern matching is a really powerful feature. And I would really recommend you using it, or at least trying out it to see if you like it, as it can lead you to really nice and clean code, and also reducing your number of bugs.
Very cool. There's a few other things that functional programming languages often have. One of the big things is recursion.
Recursion is a key concept in most functional languages. And it's a way of functions calculating their output by calling themselves, which might sound really weird, but I hope it will become clearer in a bit. We'll start out by looking at a regular imperative way of implementing the algorithm that we'll be looking at, which is the factorial. So just as a reminder, the factorial of 3 is defined as 3 times 3 minus 1 times 3 minus 2 until you reach 1. So you can see here factorial of 3 is 3 times 2 times 1 equals 6. This is an imperative way of doing it. We start out by setting the factorial to the passed-in value, 3 in our example, and then we do a descending loop until we reach 1, and we multiply the factorial by the values. So first we have 3 here, then we multiply it by 2, then we multiply it by 1, which we could skip, of course, but just for demonstration purposes, let's leave it in there. And then we have an imperative way of implementing the factorial. But let's see how that looks like in a functional language where we're using recursion. So let's define a factorial function that takes a single parameter, and it is an integer, and will return an integer. So let's recap what we had with the factorial implementation. Our example was factorial 3. So if you look at this bit of code, pseudocode, you might notice that 2 times 1 is actually the same as the factorial of 2. And 1 is the same as the factorial of 1. So another way of writing factorial 3 is to write this like that. So you can see that the factorial of 3 is 3 times the factorial of 2. And the factorial of 2 is 2 times the factorial of 1. And this is a recursive definition. So factorial result is defined in terms of calling itself. So this is perfect for our example, because we can now try and use this bit of pseudocode. So we'll omit the call and then translate it to F#. Well, we're not hard coding things here, so let's just do n and n minus 1. And this doesn't compile. And this is because F# by default doesn't allow functions to call themselves to be recursive. So you have to opt into that via the rec modifier. So this is now a recursive call. It has an unfortunate problem, which we'll see if we output the factorial. So let's try and output the factorial of 3, see what happens. And we have a stack overflow exception here. This is unfortunate, but this makes total sense, because what we haven't done is we haven't taken account for the fact that it has to stop sometime. So what we're now doing, it will keep on continue executing. So when it gets at 1, it will call the factorial of 0, then minus 1, minus 2, ad infinitum. So it will continue all the time. So what we need to do, and what you always need to do when you do implement a recursive algorithm, is to consider the base case, the terminating case. When does the algorithm, the recursion, stop? And in our case, that's very simple, it's at 1. So if the argument equals 1, then we can just return 1 as the value, because the factorial of 1 is 1. And otherwise, we can just use our regular algorithm. So this is a direct translation of the logic that we have here. Either you are in the case where the value is 1, and then you're at the end, you can just return 1, you don't have to do any calculation, or you can do the proper recursive definition. And now if we run it, we should have a working version of our code. And we have 6 here. So with that, we have implemented a recursive algorithm. This might be somewhat weird to you, and it's a fairly trivial example, but even though it's still hard to wrap your head around, what I found really helpful is to put things down with pen and paper. So just write things down, just try and put things down like this, and you can see the function calls and the arguments that are passed into the functions, and then it will hopefully help you understand recursion. And after a while, recursion will become a second nature. It's often hard in the beginning, but you will get there.
So there's lots of interesting things. I'm interested, Erik, how this changes how you think about code, or when you're writing code. What are the big things that sort of change in the way you're actually working?
I think the number one change has been that I'm now embracing immutability. So also in languages where immutability might not be the default, but where it's an option. For example, in JavaScript, you can use const. I try to use immutability by default, regardless of the language. So personally, I found that it seemed to reduce bugs. It's always hard to quantify that. And I think that's because it makes it easier for me to reason about the code. So coming back to the bookkeeping, less bookkeeping in my head. So I think the immutability is probably the key thing that I've adopted into my programming style. And I've also been moving away from objects and state more to like data and separate functions that are the behavior. So less classes and more like functions plus data, which is the functional way. And you can often work with that. You can even work with that with classes being the data. If you don't have methods attached to it, then you're sort of repurposing classes a bit. But I quite like that. And it's not an uncommon pattern in C#, for example, where you can have a class that's just like a container for objects and then have different, static methods working on it. I quite like that. And it does depend on the language. So it doesn't really make sense, for example, in Ruby, but in certain languages, I think it can work well, like C#, for example. I've also, having been exposed to pattern matching, it's been a blast working with pattern matching. So I'm very pleased that I'm now seeing more and more languages adopt pattern matching and slowly adding more different types of pattern matching cases like lists and etc. So I've really enjoyed seeing that it's becoming very mainstream now. And finally, I think if you do a functional language for a while, you start out with maybe doing recursion, etc. But at a certain point, you realize that there are just a handful of types of recursion. So iterating over everything one by one and generating a new, like a mapping, like a list, or just one value, so like a map or a reduce, is so common that all these functional languages have built-in higher order functions that basically do that for you. You just have to pass in the right functions as arguments. So we have higher order functions again, passing in functions as parameters. And it's one of the first things that I do when I check out a new language is see what higher order functions do they have, which is to me like an indication of will I be able to use my knowledge that I already have from other functional languages, because they're often very similar between languages. So learning one functional language means you get this whole other functional language. They become a lot easier because they usually have the same types of functions, maybe slightly different names. Yeah.
So, functional programming has become really popular again in the last few years. There's a wide range of languages that are functional. You've talked about picking new ones up. There are languages like Haskell that lots of people have a fear of and a bit of a dread about. Some like Lisp that are intriguing, but often perceived maybe as not very real world. That's something we'll be coming back to with a dedicated Lisp month later in the year where we can put some of those perceptions right. Then there's newer languages, I guess, like Elixir and F#. that have maybe made programming and functional programming more accessible to everyone. There's a new functional language called Gleam, which we've just launched literally today on Exercism. Do you have favourites, Erik? How do they differ? Which ones would you maybe recommend to someone who's wanting to explore functional programming for the first time?
Yeah, I have favorites, of course. As you might have guessed, based on the examples that I've shown, my personal favorite is F#. It's not the language that I started out with, but it's the language I quite like the best. And there's a couple of reasons why I think it would also be probably a very good choice if you start out with functional programming. For one, its syntax is quite nice. I think it's clean. It has a lot of features, but it's not too overwhelming. So you also have other functional languages that provide everything in the kitchen sink or whatever the expression is. There's like a ton of things that you can do and a whole lot of features that you might not ever need, and definitely not as a beginner. And F# doesn't do everything, which is a very conscious decision. And it has very good documentation. And I want to plug the F# for Fun and Profit website, which uses F# to teach functional programming. So it's basically perfect for if you're starting out with functional programming, because I think it's both well written and it's also somewhat funny at times. It has nice images, etc. So it's a great resource, and it's very thorough. So you find everything from basics to more advanced concepts, but especially the basics. I use it a lot when learning F#, and I found it invaluable in improving my functional skills too. So I really like that. Another benefit of F# is that it has, especially for a functional language, a very good tooling. So if you use Visual Studio or Writer or VS Code, there are great plugins for F#, and of course in Writer and Visual Studio they're built in. But you get code completion, you get very nice syntax highlighting, you get these little type inference thingies where it shows you the type if you let it type infer for you. And I think as a new developer, that's really helpful if you can just sort of explore things via your IDE. And but maybe the best reason for starting out with F# is that it's a functional first language. It means that it wants you to try and solve things in a functional way, but it doesn't force you to. You can also do imperative/object-oriented programming in F#, so that's fully supported. You can use Immutability. You have to opt into it. But the biggest advantage of that is that you can start out with doing things in your old imperative object-oriented way, and then slowly convert that code to functional code, which to me is an easier way of getting started. So enough about F# and my love for F#. Another language that I really like is Elixir. It has Ruby-inspired syntax, but then applied to a functional way of programming, whereas Ruby is very object-oriented. So that's quite fun to see. It runs on the Beam VM, which is like what Erlang runs on. And this gives it fantastic concurrency/fault tolerance features and everything that goes with the Beam, being able to scale, etc. It also has very good tooling. And very importantly, it has one of the best Exercism tracks. So there's a dedicated learning mode, so where you can learn most of the concepts that are in Elixir, and they do it in such a fabulous way that I would really highly recommend people using it. I've done them all myself. It's just a blast. They did such a great job. And then you mentioned the new language like Gleam. I really like Gleam. It's fairly new. I don't know the actual version, but it's still very new. It's in active development. It has very nice syntax. It's sort of like it takes ideas from different functional languages and it takes the best ones. So I think it's a very, very good pragmatic language. And like Elixir, it also runs on the Beam VM. So you get all the same Beam goodness that Elixir gets for free. And it's also interesting that it's actually built in Rust. So Rust is a non-functional language by default, but Rust also has a lot of functional features. So it's interesting to see that implementing a functional language in a non-functional language still gives you functional stuff. So quite like Gleam. So do check it out. You can, starting today. And then finally, I would, not finally, the next to last one is I have to mention Haskell. Haskell is probably the most pure functional language out there, which means it takes all the purity, the pure function stuff, and takes it to almost to the extreme. Everything is pure. Side effects are disallowed. They're sort of baked into the type system. There's a certain way you have to deal with them. And that makes it incredibly pure from a functional standpoint, but also somewhat hard to start with. But it has great features. You also have lazy evaluation, which means that it will only ever evaluate stuff that you're actually using. So expensive calculation that you're actually not using, it will just not do them, which can be mind-boggling when you start out that. It has very advanced type system with type classes and some other things that I'm not going to even mention. But if you know a bit of functional programming, so you have a functional language under your belt, this might be a great second language because it's basically everything that you can think of in a functional language is there. And then I really like Clojure, which is also a functional language, but it's a Lisp. So I'm not going to talk about that. We're going to talk about that as part of the separate Lisp-based month. I think it is June or something like that. My final point is that you can do functional programming in a lot of non-functional languages nowadays. So languages like Rust, C#, Kotlin, Java, they all borrow literally from the functional paradigm. So there are a lot of functional features that you can use in those languages. So functional programming in a way is already becoming mainstream. So I quite like that. I can use my functional programming skills and apply them to new languages. So I'm quite pleased with that. Yeah.
Awesome. Thanks for going through all this. So that's our introduction to Functional February. Over the rest of the month, we're going to be streaming people solving exercises on Exercism using functional languages. And so if you're interested in seeing someone like Erik, maybe even Erik, solving these exercises, you can subscribe to our Twitch and our YouTube channels and keep an eye out for when we're streaming so that you can watch people doing them, come into the chat, ask questions, and just generally join them. Please give some exercises on Exercism a go yourself. Functional programming is fun, it's interesting. If you've not done it before, it's going to be a really eye-opening experience. Thank you for watching. Have a really fun day.